Now that we've all set up, let's figure out the values of our variables. Besides the constant gravitational acceleration, we are told that the initial velocity is 20 meters per second. But we have to be very careful here. The baseball is thrown upwards, but we chose downward as the positive direction. This means our initial velocity must be a negative value. So our initial velocity should be negative 20 meters per second. Then we also know the time for the entire journey is 5 seconds. So delta t is 5 seconds. What we are solving for is the window above the ground, or in other words, the initial height of the baseball, which is the displacement from the initial position all the way to the ground, which is the final position. So this is delta B. Now let's bring our kinematic toolbox and pick the right tool for the globe. Let's check these kinematic equations. And this third one looks good to us because it uses the initial velocity, delta t, the acceleration, and delta t again to solve for the displacement, delta d. Now let's copy it. Delta d equals to the initial velocity multiplied by the delta t plus 1 over 2, and the acceleration in our case is the gravitational acceleration, g, and then delta t squared. Some of you might be thinking, wait a second, won't this give us the total distance of the baseball traveled, like going up and then back down? And the answer is big no. This equation solves for the displacement. Remember, displacement only cares about the starting point and the ending point. It doesn't care about the path taken in between, right? So using this equation, we'll get the initial height of the baseball rather than the total length of its trip. For the rest, it's easy. Let's plug in the numbers. So delta d equals to the initial velocity, vi, is minus 20 meters per second. Then delta t is 5 seconds plus 1 over 2. G is 9.8 meters per second squared. Then times 5 seconds squared. So it equals to 22.5 meters. So the height of the baseball is 22.5 above the ground.